Okay, so in the last lecture, we just finished talking about Constexpr variable requirements in a little bit more detail. You were introduced to Constexpr variables a while back, but now that we were introduced to literal types and so on, we can look at things a little bit more detail. What I want to do now is just go through some code examples and kind of point out some illustrations of the particular rules that we were introduced to at the end of the last lecture, just to show how they can be violated and so on. So in this particular code example here, we have a bunch of Constexpr functions, Constexpr variables. The first one is not a valid Constexpr variable. The reason why is that if you go and look up the string type in the standard library, the properties that it has are not, it's such that it's not a literal type. And again, the only types of variables that you can make Constexpr are variables that have literal type, or are of a literal type, I should say. This particular Constexpr variable here, this is not valid. I mean, int is a literal type. It's basically a built-in scalar type, but it's not being initialized. I mean, if this was valid, essentially what we've done is we've created a variable at compile time called I, and we've initialized it to random garbage that we can never change, right? Because when things are Constexpr, they're implicitly const. We can't change them afterwards. So it's got random, like an undefined garbage value, and we can't change it, which would not be useful. So the language just forbids this. The last example that I have here, this would be an invalid Constexpr variable. The way it's basically being initialized is the problem. We have this function func. This is not a Constexpr function. It's just a regular function. So on the right-hand side here, the thing we're trying to use is the initializer for the Constexpr variable that we're creating. Is something that in principle can't be computed at compile time. So you're trying to say, fix the value of f at compile time, but I'm not going to tell you at compile time what the value is because you have to run the program to figure out the right-hand side. This is not going to work. So this is the reason why this kind of thing is forbidden. Any questions? This slide just kind of goes on and it lists off all the different requirements for Constexpr functions. You don't need to memorize these things or anything like that. And actually, a lot of these things for the purposes of this course are not important, in the sense that you're unlikely to violate some of these properties because of the sorts of code you're going to be writing. But I tried to kind of highlight the ones with stars, which are maybe the more likely ones that would maybe trip you up. So I'll kind of focus more on these particular items rather than some of the other ones. So in order for a function to be a valid Constexpr function, there's certain requirements that need to be satisfied. There's like lots of things that you can't do in Constexpr functions. One of the things that's quite important is the return type has to be a literal type. I mean, you'll see like a lot of things have to be literal types. This is the reason why I needed to define what a literal type is. Otherwise, you just stare at me blankly when I say this has to be literal types. Like, huh, what's that? So literal types are quite important when you're doing compile time computation. Additionally, all the parameters of the function also have to be a literal type. I think we talked about this the next bullet item when we were introduced to Constexpr functions, which is that when you say Constexpr, what you're saying essentially is not that the function is going to be computed at compile time. What you're saying is, in principle, theoretically, for some choice of arguments that I could pass to the function, it's possible to compute this function at compile time. So if you give it a function that you know, theoretically, you could never compute at compile time, this is not a valid Constexpr function, because Constexpr is saying, for some choice of arguments, it must be possible to compute this at compile time. So if you give it a function where categorically it can never be computed at compile time, this is not a valid function. So that's essentially what this particular bullet is saying. Then it goes on and says, like, there's a bunch of things that, if you have like an interesting body to the function, it can do pretty much anything except for this long list of things that it can't do. And you can't have like assembly statements, for example. But anyway, we're not going to be doing assembly directives. The more important things are the ones I've marked with stars. So you can't define local variables that are not literal types. So like the variables inside the function have to be of literal type. You can also you also have to make sure you initialize variables. You can't define a variable and then not initialize it. And this often trip you up until you get used to it. You kind of, because maybe you have a variable and then later on you're going to initialize it before you use it, so you don't bother to initialize it, but you have no choice. You have to initialize it. Even if you're going to redundantly initialize it, like you write the value, it's just like a dead store. You never actually read back the value, immediately initialize it with something else. It doesn't matter. You still have to initialize the variable. This might get relaxed maybe in C++ 20. They're talking about a lot of things to maybe kind of relax things a little bit more with respect to Constexpr. That's interesting. Don't know if it's my notebook or the projector. I've sometimes had the projectors just kind of spontaneously turn off. Well, I'll try to see if it makes any difference if I reconnect. No, I don't think it's probably my notebook. I think it might be the projector if it doesn't come to life. Okay. Anyway, I don't know if this is still recording or not. Anyway, to the people who are later listening to this video, I don't know what happened to the projector, but at least things seem to be working now. Anyway, so getting back to the material, I guess we're talking about this bullet here. So basically, you have to make sure you initialize Constexpr variables. And again, like there's a lot of other stuff here. And for some of the earlier slides too, there was more detail than what's necessary. Really, I'm just trying to give you a sense of, like, I'm not going to quiz you and say, like, what are the different properties or that the function has to satisfy to be a valid Constexpr function. But some of the more basic ones I would hope you would understand, because if you don't, you're good luck with doing the programming assignments because you're never going to get things to work. But there's a lot more here than what you need to know, so don't worry too much about that. Just some examples of things, violating various different requirements for Constexpr functions. This is what this slide's trying to illustrate. So the first function that we have that's Constexpr here, this is not a valid Constexpr function, this get_value. The problem is the return value is a std vector of int, but std vector is not. It turns out if you go and look up the properties of the type, std vector doesn't satisfy the constraints of a literal type. I mean, kind of the giveaway of this, anything that might do memory allocation, for example, in the constructor, which is then going out to deallocate it in the destructor, it's not going to have a trivial destructor, therefore it's not going to be a literal type. And you can kind of guess std vector is going to have to allocate memory. Similar kind of problem with std string. So here we have a parameter being passed to a function, but this parameter that's being passed is not a literal type. The parameters also have to be literal types, the return value as well as parameters. So that's the reason why this is not legal. The next line here, this comes back to kind of fundamentally what Constexpr is saying. When you put Constexpr in front of a function like here, what this is saying is, in principle, there are some choice of arguments that I can give to this function such that it is possible to compute it at compile time. But this function here, even if I give it a literal, like I call this function like with 42 in my code. So like obviously I know at compile time what 42 is. It's 42, an integer literal, an integer constant. But the thing is, this code can never execute. The body of the function is the problem. It can never execute at compile time because look at what it's doing. It's outputting to cout. How do I know at compile time what cout is going to be? Like it could be redirected anywhere, right? Like so there's no way that this could ever work. So like this function categorically could never be called at compile time. So it would be flagged as an error if you try to say Constexpr because the compiler can tell by the body of the function that you're lying, and the function could never be called at compile time, even though you're claiming that it can be sometimes. The next example here, and this is a very common sort of mistake, which I'm sure will happen to a lot of you. Here we have a local variable I, but we haven't initialized it. And it's irrelevant if later on you initialize it before you first use it. It's not good enough. You have to initialize it at the point that you use it. So this is not allowed. This is something that might possibly be relaxed in C++20 as I understand it. But anyway, the reason for doing this is it avoids the possibility of undefined behavior, because a lot of these constraints that are placed on the Constexpr code that's running at compile time is to avoid undefined behavior. Because maybe when your code is running, you don't care if you have undefined behavior. You should. But maybe you say, I failed the course. I don't care, whatever. My code can do whatever. However, the compiler writers, they don't want their compiler to have undefined behavior. And because they're running your code in the compiler at compile time, they don't want you doing anything that could have undefined behavior, because when it does, it will probably crash the compiler, right? And then, unfortunately, you who should be getting the bug reports, because you're writing the crazy code that's crashing the compiler. But of course, that's not how it works, right? The bug reports will be filed against these poor compiler writers, and then they're having to say, well, sorry, it's not what we're doing. It's like you're being an idiot. You're feeding it code that's not valid. So a lot of the things that are constraints that are placed on you to avoid certain types of undefined behavior, and perhaps one of the most common types of undefined behavior is you use an uninitialized variable. So by always requiring you to initialize variables when you create them, it avoids the possibility of one type of undefined behavior, which is you could never have the possibility that a variable is uninitialized when it's running at compile time inside the compiler. Anyway, so that's maybe a little bit more than what you really need to know, but if you know that, it might help you to understand the bigger picture a little bit better. Let's see what we have here. Oh, again, here we have a local variable, which is not a literal type. Std vector has to allocate memory. Because of this, it doesn't have a trivial destructor, and because of this, it's not a literal type. And then at the last example that we have down here at the bottom of the slide, here this function count, it has a static variable. Static variables, they basically have their state persists across function calls. The very first time you hit the function, I is initialized to 0. After that, it's not initialized again. It retains its value, and then you can modify it. So it persists across function calls. A state that persists across function calls would cause problems with respect to compile time computation, because what value should it have at compile time compared to runtime? So it would be problematic. So this is not allowed. Constexpr Constructor Requirements. So constructors can also be marked Constexpr. Technically speaking, they're not member functions in terms of like legalese in the C++ standard, at least as I understand it. But for all practical purposes, you can think of them like a member function. But they have some constraints as well. If you're trying to make a constructor Constexpr, if the type itself that you're trying to make the constructor Constexpr for doesn't satisfy certain properties, it's a no-go from the beginning. Forget about what you do in the constructor code. Like if the type doesn't satisfy certain properties, you can't have a Constexpr constructor. In addition to this, there's other properties which are mainly the ones that are associated with member functions, like all the properties that functions have to satisfy in order to make them Constexpr. The same sort of carries over to constructors. But in addition, the type itself that the constructor is associated with has to satisfy some constraints. So I'm not going to go through all of these in detail because some of these are definitely not going to impact you in this class. You're not going to have virtual base classes in this class for sure. So you can ignore stuff about that. Anyway, each of the parameters of the constructor have to be of a literal type, just like you have in the case of parameters to member functions. The other one I want to comment on is this one here. So the constructor body, like the actual code that you're writing in the body of the constructor, it has to satisfy all the constraints that are satisfied for a regular function, like a member function that you're calling, which sort of makes sense. Because again, it's kind of like a member function, but the constructor is kind of like a member function, but not quite in the sense that the standard doesn't view it that way. Anyway, that's all I want to say about Constexpr Constructor Requirements. Again, there's more information here than what you need. And if you're really a masochist, you can click on these links and you can go to the part of the standard that actually describes these things, and you can read them and start to cry. Or you won't ever want to look at the standard again, probably. Anyway, just some examples to maybe illustrate some of the things that was pointed out on the slide we were just looking at. So here we have this class called widget. And then we have some Constexpr constructor for it. This is not a valid Constexpr constructor. The reason why is this class has a data member called I underscore, and we're committing the cardinal sin of we're trying to create a Constexpr thing, but we're not properly initializing it. In the case of creating an object, this means we have to initialize all its data members, but we're not actually initializing anything. And by the way, typically, when you're doing Constexpr code and you're writing constructors, you're probably always going to have almost always going to have initializer lists. So if you don't have an initializer list for your constructor, that's a giveaway that maybe you're going to have problems. Not always, but often you will need them. In this particular case, if we don't provide any way to kind of initialize I underscore, what's happening will be default initialize, like initialize in sort of default way, which is for a built-in type, don't do anything. So I is left uninitialized. So anyway, so this is the reason why this complains. Here we have a parameter that's not a literal type, so we're trying to have a constructor parameter that's a non-literal type. Down in this case below, remember, we're not going to really do much with inheritance in this course. There's one assignment, there's some code that's given to you that already uses inheritance kind of for you to make your life easier. I'm sure some of you, well, I'm sure a lot of you have used inheritance in some language, maybe not necessarily in C++. But anyway, don't worry too much about inheritance. But I'll just use this to kind of illustrate the point, because I'm sure a lot of people are at least familiar with the notion of inheritance, if not in this specific language. Here we have a derived class, which is inheriting from base. So in order to create an object of type derived, obviously we're going to have to create an object of type base. In the case of the derived class, we do have a Constexpr constructor, so we're good. At least it looks on the surface like we can construct one of these things at compile time. However, in order to construct one of these things at compile time, we're also going to have to construct the base class object. But if we look at the base class doesn't have a Constexpr constructor. So the base class categorically be created at compile time. Therefore, we cannot create anything that derives from it because we won't be able to create the base class object that's contained in that object that derives from it. Anyway, so this is what the problem is here. It's not actually, the problem is not immediately in the derived class, but rather in the class that it's inheriting from. And this slide maybe I might talk about in the tutorial. It's kind of not really as important, relatively speaking. This slide here illustrates the various different things that can go wrong with respect to Constexpr functions that access state that's external to the function. And what I mean by this is you're accessing things that aren't local variables to the Constexpr function. Often this is going to be problematic. So for example, here we have a Constexpr function where we have a static variable, a static variable internal to the function. This has state which persists across function calls, which is problematic. Because when you're doing compile time computation, effectively what you're doing, you're taking code that would run at a particular point at runtime, and you're moving to compile time. You're changing when it runs. Now, when you change when it runs, there's some state that could have different value when you move it from one point in time to somewhere at runtime, somewhere at compile time. Obviously, this could cause problems, right? If there's some values that could change, because then by changing when the code is run, you're actually causing it to compute a completely different result, which is probably not what you intended. The idea is you wanted to compute the result at compile time, but you wanted to compute the result that it would have computed at runtime, but at compile time. You don't want to compute a completely wrong answer, which is different from what you wanted. So this is kind of the reason why you run into problems when you have a dependence of the result that's being computed on a state that's external to the function, because that state is often something that's not going to be very well defined. So this is basically the problem here. You don't want to have static variables in a Constexpr function. Here we have a global variable, which is not Constexpr. So at runtime, its value can change. It could be modified. And then in this Constexpr function, we're trying to mutate the value of this global variable. This is not really going to be very well defined. The global variable doesn't even exist yet at the point at compile time when we're trying to modify it, right? Because the variable is initialized. It's a runtime thing. The value of this global variable would be initialized at runtime when the program first starts running. So if you ask me what it is at compile time, I don't know. Who knows? The compiler doesn't know either. So this wouldn't really make much sense. So here we're trying to modify a global variable or some kind of external state. In the last case here, we're just trying to access some external variable. So we have a global variable. It's not Constexpr. It would be a different story if it's Constexpr, because then the value would be fixed at compile time. But it's not Constexpr. So its value is initialized at runtime, and it could change from the value 2. Its initial value when the program starts up would be 2. But of course, it can be mutated because it's not a constant variable. So this would not be a very well-defined function if it was allowed to compile, because it's using alpha. But at compile time, what value should it use for alpha? Alpha doesn't exist yet because it's created at runtime, initialized then. But even still, if you say, well, I'll use 2, well, yeah, but it might not be 2 by the time you actually get around to using the value. So it's not really well-defined, so this is not allowed either. I mean, generally speaking, you can't use global variables in Constexpr functions, either reading them or writing them, because it would lead to a lot of problems like what I'm describing here. Any questions about that? Constexpr and immediate initialization. So kind of coming back, I'm going to harp on this a little bit because in particular, this sort of scenario here is kind of a little bit more subtle, but it often will trip students up. Here we have a template class. It's just some kind of data buffer. So the only data member it has is an array, where T is, if we look down below the code that's actually using it, it's plugging in char for T. So it's just like an array of char. It's some kind of character buffer. And then we're going, oh, well, we want to be able to create one of these things at compile time. So we create a Constexpr constructor for it, a default constructor. And actually, probably I should look at the part that's commented out, because that's really what I want to comment on is the error. This will be fine, what's actually here. But suppose that we wrote the function like this. So like lines 9 to 12. Suppose that we delete this line 15 and replace it by lines 9 through 12. This would fail to compile, and the compiler is going to complain saying, you haven't initialized it. You're not trying to fully initialize this thing in the constructor. And the issue is that we've not specified any initializer list for the constructor. So what happens, whether you want to ignore it or not, the reality is this is what happens when you construct an object before you ever hit the body of your constructor. So before we hit this left brace and execute what's inside of it, lots and lots of stuff happens. And the stuff that happens is all your base class objects are constructed. In this case, there's no inheritance, so there's nothing to do there. And all of your data members are also created and initialized. So effectively, when we hit this left brace bracket here, this data underscore thing has been created. And the default, since we're not specifying any initializer list, it turns out because of the rules of the language, because the array is an array of a built-in type, the default behavior for initialization is I do nothing. It's just uninitialized. So effectively what we have is we have a buffer that's uninitialized. It's not acceptable that we later change it. We go, oh, I didn't initialize it. Give me a do-over and let me initialize it inside the body of the constructor. It's too late then. You've already created uninitialized by not having an initializer list, and then you get a compiler error. This is maybe the situation where it's more likely to make you scratch your head a little bit more, because you might not realize, you might have a bunch of data members for your class and you might not really realize what's happening. And I noticed, at least last year when I taught this course, Clang, in this sort of situation, Clang had like a very kind of cryptic error message that a student showed me. Like the problem was basically like this, like they had some kind of array type, a built-in type, and they didn't initialize it, but the message was not anything that would ever lead you to suspect that that was what the problem was. It was some weird thing. I don't know if they've maybe improved that error message from before, because that was like a year ago. So there's been some major releases of Clang since then. But anyway, this is another reason why I provide 2 compilers in the course. If you're compiling things and you get some kind of weird error message that you can't really make sense of, it's worth a try. You can try it with the other compiler, see what happens. Sometimes, and I can't, and in spite of the fact that I saw this weird thing with Clang, I mean, it's not fair to say like, GCC always has better error messages than Clang. Actually, a lot of cases, maybe Clang has better error messages than GCC. But basically what I'm saying is if you have problems with one compiler, you might try the other one, because if it gives you a more enlightening message that helps you, I mean, it's not hard to change the compiler that you're using, especially when you're using CMake. So it is worth a try anyway. So I want to say anything else? I guess that kind of illustrates the main point here. So be particularly careful, like if you're creating objects in a Constexpr constructor, you need to be sure that all the data members get initialized. And if you're doing inheritance, then you have to make sure base class objects are initialized as well. As for debugging Constexpr functions, I want to talk a little bit about debugging Constexpr functions. Constexpr code, compile time code, is a bit of a pain, at least with the state of the language as it currently is, to debug. Because when you want to debug code, like what's the first thing that typically people do? You don't break out GDB, like you don't break out your source level debugger, because we're lazy. So the first thing we do, we add a print statement, right? That ain't gonna work, because once you add a print statement, your code can categorically not run at compile time. It's not Constexpr, you're toast, because you can't do I/O at compile time. This might be something in C++ 20 or some future version of the standard might change, because I know a lot of people said, like, shouldn't there be some mechanism where you can output some kind of error message or something, or some kind of debugging, formatted debugging output at compile time. But at least in C++ 17, which is what we're using in the course, what happens later, that doesn't help us. The state of the affairs right now is that you can't do print statements of any type, really. So what can we do? There's not really any super great solution, but there's kind of various degrees of badness. So what I'm going to do is just kind of highlight some of the choices that you have, and then you can pick whatever works best for you. Or probably the most realistic thing is a combination of these things, combination of these strategies. Obviously you can't debug the compile time code with a source level debugger, even if you wanted to, right? So it's not a matter of laziness here, like, oh, I really don't want to type GDB and fire up my source level debugger. Well, I guess in principle you could do it, but the thing you're debugging, you're going to be debugging the compiler, right? As it runs your code, you're stepping through the compiler. Good luck with that. And compilers are like immensely complicated programs. So a source level debugger is not going to be very helpful, because we're basically going to be debugging the compiler as it is interpreting our code, which is not very useful unless you happen to maybe know Clang inside out and backwards or GCC. And again, we can't add print statements, so that's not really a very viable approach. One thing that we might do, sometimes works, is that you might write all the code, test it, debug it, but not make it Constexpr yet. So like basically leave all the Constexprness out of the code, get it working, and then as a last step, just put Constexpr in and pray to God everything still works after that. And this will work. This is a good strategy in a lot of cases. The problem with it, though, is what happens if the code that you want to test is such that you have to do some of the computation at compile time, because you have to assign it to a Constexpr variable, for example. Well, then this approach won't be viable. Like if you really do need to do the computation at compile time, you're basically saying, well, my solution is I'm not doing it at compile time. I'm going to leave out the Constexpr. So it will work. It's okay in some situations, but there will be some situations where clearly this is not a viable solution, because you actually fundamentally need to do the computation at compile time. But it sometimes works for some things, and it might work for some part of some of the assignments in the course, for example, that use Constexpr. Another approach is you can use assert. Assert is defined in a very particular way. Assert is defined such that if the expression that appears in the assertion evaluates to true, then assert true is a constant expression. In other words, it's something legitimate to use at compile time because it's a constant expression. The compiler knows what is at compile time. However, if it evaluates to false, it's deemed to be not a constant expression. So then your Constexpr code immediately becomes invalid code then if you're trying to call assert false because you're trying to do something that's not Constexpr inside a Constexpr function. But this kind of gives the behavior that you want, because what you would want to happen if you do have one of your assertions fail in a function that's being run at compile time, what you probably want is the compiler gives you an error message at compile time saying, hey, things are not working. And this is what will happen, depending on how the compiler is in terms of the quality of error messages that you get. You might get a variety of different things, but most likely you get something to the effect that, well, it's a minimum to the effect that assert is not a constant expression. But maybe you might get a little bit more useful message, which is that, basically the thing that you're trying to say should be true is not true. Like essentially one of the conditions you're testing for is not valid, and this is why I've stopped your program from compiling. But if you see the assertion failing and you get some kind of message, then well, at least you can probably very quickly deduce that whatever condition you're testing has failed and something's wrong with your code at that point. So assertion is a good tool. Another possibility is you can also throw exceptions. And the way that this works, you can't actually throw exceptions in code that runs at compile time. But as long as it's not actually running at compile time, you can throw exceptions. So what happens is if you have a function, for example, it's just like a single line throw, well, this is not a valid Constexpr function because categorically it can never run at compile time because it's always throwing. But what you could do is you could test the condition that it would be indicative of an error, saying like, if something is true, meaning that there's something posed in my code, then I throw. And if you have a throw statement in your code, but it never gets hit at compile time, this is fine. It's your function is still valid Constexpr code. If, however, it hits the throw statement, then this is not valid and the compiler will complain. But this is probably what you wanted anyway. They will complain at compile time saying, hey, you're trying to throw an exception. Throw is not a valid statement in Constexpr code because it actually hit the line in the code that would actually throw the exception. So exceptions kind of work because of this sort of property. Like you can have throw statements in the code. It doesn't immediately disqualify the function from being able to run at compile time, provided that it doesn't categorically always throw. Like in other words, as long as you don't hit the throw statement, it's okay. So basically the way you would use this, you use an if statement that would test whether something is wrong with your code, testing some kind of maybe precondition or whatever, and then throw an exception if that error case is detected. So basically, kind of summarizing, you have like, the main viable approaches is maybe you don't do Constexpr at all, and then add it in at the end, if that's a viable approach. You can use assertions, which would probably be what I would recommend, or you can throw exceptions, or you could use a combination thereof. Actually, the combination thereof probably is the best strategy. But unfortunately, you can't really run a source level debugger, even if you wanted to, because you're going to be debugging the compiler, and you can't do print statements, which is maybe the most annoying thing of all. And maybe coming back to a question that was asked in the last lecture, I don't remember who asked it, but someone said, well, would you maybe want to make all your pure functions, make all of them just Constexpr? Well, if they have print statements in them, you can't. So like there might be some reasons that you can't do this. Well, I guess actually, sorry, then it wouldn't be a pure function in them. But there might be functions that the only thing kind of preventing them from running at compile time is the fact for some reason you might want to do some printing typically, and then you wouldn't be able to do things in that way. Anyway. So just to maybe give a concrete example of this sort of strategy, like so maybe I'm writing a square root function that I want to run at compile time. So I've made it a Constexpr function, and I want to make sure, for example, that the thing I'm being asked to find the square root of is greater or equal to 0.0. So like it's basically not a negative number. This is probably testing a precondition of the square root function. Most likely it's basically specifying that you can't give it a negative number. So being a diligent programmer, the person has said, I want to check the precondition. This is a valid thing to do because assert, basically, as long as the thing is true, asserts true, what will happen is this is considered a valid constant expression, this line of code. Therefore, it doesn't cause any problems with respect to compile time execution. If it evaluates to false, basically, then the function is not a valid function, but it's okay. It will give you an error. That's what you want because the code is obviously wrong if the precondition's been violated. Another example is this function foo down below here. So suppose that you have, for some reason, it turns out like there's some code here which I've left out, this ... But for some reason, suppose that if you get to this line here and I is an odd number, it's an indication something really badly hosed with your code. So you might do something like you check to see if it's an odd number. If it's an odd number, you throw an exception. This is a valid Constexpr function because if it always threw every time, no matter how you call it, it always would throw, then it wouldn't be valid because you could never run this at compile time. But this is valid code because it only throws if this condition is true. So presumably this code could run under some circumstances and this condition is not true, in which case it wouldn't throw, in which case this would be a valid function to run at compile time. Therefore, it would be valid to make it a Constexpr function. So this is kind of the mechanism by which things work. So these are the two strategies with respect to assertions and exceptions that you might use in your code. Again, I don't want to be too prescriptive. Use whatever you find to be kind of the most effective for the code you're developing. But it is a bit of a pain that you can't do print statements. They would be very convenient. Any questions? Okay, so we'll get into some more code examples here. So this is similar to some of the code examples I went through before. So the idea here is we have some sorts of problems. These are problems with respect to Constexpr. And I just want you to take a look at the code. Basically, don't look at the next slide because the answer is on the next slide. But what's problematic about this particular code here? Anyone want to take a guess at this? It kind of has to do with where things are in terms of how things are distributed across various different files. Well, let's imagine that we're the compiler, and we're compiling app.cpp at the bottom. So the particular translation unit that's being compiled in C++ speak, the translation unit we're compiling is app.cpp. So the compiler sees this line here. We're trying to call the absolute function with the value -42. So when we're compiling this translation unit, the only thing it can see basically are the header files that we either directly include or transitively or include by indirect inclusion through other header files that these header files include. So to make a long story short, what we see is this, or what the compiler sees is this. So it sees, okay, we have a Constexpr function. ABS is a Constexpr function. So kind of like in principle, yeah, I should be able to call this in compile time. Great. Okay, let's evaluate at compile time. Well, what's going to happen here? How do I do this? Right? Can people see what the problem is now? You don't know what the code is. The compiler doesn't know what the code is. You're saying compute the ABS, and you've kind of dangled a bit of a carrot in front of the compiler going, hey, you can do this. You can do this in compile time. And then it goes to do it. It goes to actually compute the result from this function. It looks for the declaration of the function to figure out what should I do. You didn't give it, or sorry, the definition of the function to see what it should do. You didn't give it the definition. There's no body to the function. You've only given a declaration, which is bad. So, I mean, basically the problem here is that the definition which appears in this foo.cpp file, this definition should be in the header file. And remember, Constexpr functions are implicitly inline. So basically the kind of rules that apply for inline functions apply here. And we had a similar code example that illustrated this kind of problem for inline functions in a previous lecture. So it's the same sort of issue here. So because Constexpr functions are inline, you're going to want the definition to be visible when those functions are being called. Otherwise, you're into a lot of problems. Anyway, so that's the problem with this code. What's wrong with this code? Well, what's wrong with this code? Well, actually, if you compile it with GCC, at least the last time I tried GCC with 8.3, again, I haven't tried 9.1 very much, but I suspect probably the story hasn't changed. GCC, in violation of the language standard, defines square root, sin, and cost to be Constexpr functions, but they're not actually Constexpr in the standard. And the standard actually says, like, thou shalt not make things Constexpr or whatever, like if I don't say to do this, because it causes problems if things are unexpectedly Constexpr. So the problem here is we're trying to call it, I mean, it looks all well and innocent, and you might think, I mean, it would seem kind of reasonable, right? Like, square root shouldn't really rely on any state other than x to compute square root, and similarly for sine cos, but unfortunately this is not the reality because of this thing called errno. For those of you who maybe either C or C++ programming, you're familiar with the global variable errno, E-R-R-N-O. Some of these functions can set errno, depending on whether if you pass in some invalid parameters to the function. This caused like no end of grief for so many people in the history of C and C++, the fact that you have this errno, because it caused like lots of problems, not just in compile time computation context, but just the fact that you have a function that that sets this global variable. If the things are multi-threaded, then you have to worry about, well, now you have to make this global variable like per thread, and it creates like lots of things. Anyway, the standard says that this shouldn't work. So it shouldn't work. The solution is, well, don't use square root sign and quotes from the standard library, which is not a very acceptable solution, but this is the reality we're faced with for now. I'd be very surprised if in the future version of the standard, maybe even C++20, it's very likely, I think, they'll eventually make these functions required to be Constexpr functions so that you can call cos and sine and tan and so on at compile time. By doing some tricks, I mean, they can't just make error no maybe go away, but there's some tricks that they can maybe do if this is implemented with the help of the compiler. But anyway, for now, it doesn't work if you compile with Clang, which properly follows the standard. So in the assignment, which involves Constexpr computation in this course, this is the reason why you're required to use Clang for that particular assignment, because actually part of the assignment is, I think you're implementing sine or something. You're implementing some of these functions yourself, just using some simple formulas and things like that. It would kind of defeat the purpose of the assignment if I just let you, call the function from the library, which shouldn't work, but it does because GCC violates the standard in this regard. Anyway, enough said about that. One more example. Since this is kind of a relatively simple thing, what's wrong here, I'll just maybe comment on it. The problem here, if a Constexpr function, we're creating this local variable called result, but we're not immediately initializing it. It's not good enough that we can say, like when we look at the code, we can see it won't lead to undefined behavior because we will always initialize result before we use it because we're initializing it on the very next line. So there's no possibility we could read it before we have written the value. So in this sense, we can look at it and say there's no undefined behavior here. But just to be extra cautious, when they added the functionality of compile time computation to the language, to be extra safe, they just said, we will never allow anything to be uninitialized. Like, even for the briefest instant, things cannot be uninitialized. So this is unacceptable. So the solution is we just add like a result equal 1. We actually initialize it to 1 on the line where we're creating the actual variable. But anyway, it's sometimes maybe a little bit annoying if you have to initialize it to some value and then it just kind of becomes a dead store. Like you initialize it even knowing that you're going to reinitialize it to some other value just sometime after without ever using the value that you wrote. But nevertheless, you still need to initialize it. So that is that example. Oh, sorry, there's a question? Yeah, back up here.
So I know that in C++ you can overload function names.
Yeah.
Is it possible to do that if one of them is, say, Constexpr?
You can overload if things are Constexpr, you can still overload those functions, but you can't overload on the Constexpr-ness. You can't have like a Constexpr version of a function and a non-Constexpr version of a function, to the best of my knowledge. Another annoying thing is that there's no way to tell whether your function's running at compile time or not. This is something that they're going to add to C++20. It's one of the very first things that I really wish that there was when I started using, well, aside from the fact it would be really nice to have print statements inside of Constexpr functions. The other thing is that it's actually not any reliable way to be able to determine whether your code's running at compile time or not. Which would be nice because you might want to kind of special case things depending on if your compile time use one algorithm, runtime use a different algorithm or something like that. But that's coming in C++20. Anyway, did I answer your question? I know I kind of went on a bit of a tangent there. Okay. Any other questions? Yeah.
So with Constexpr, when you're compiling like a numeric value like this, it's going to use whatever the value is on your architecture. I feel like cross-compiling, are there any strange things can happen if like the compiler has like a different size for the standard types than what you're compiling for?
I guess for this reason, I mean, I'm not sure what exactly the standard requires in this regard, but I guess if you're doing cross-compiling, maybe it would have to, I don't know if you necessarily have to generate exactly the same results that the processor would generate, but I think you'd have a very hard time making things work if the types weren't fundamentally the same size. Like if the compile time computation was using, because the things would have to match in terms of the size, like the basic kind of properties of the types, like their size and so on. I don't know if it requires that the exact, like if you're doing floating point arithmetic, whether it would require that you compute exactly the same result that you would have computed on the processor, because there can be slight differences between implementations, the algorithms that they use for floating point that might lead to very slightly different results due to different round-off error. At least that's my understanding of the IEEE standard that's used. Anyway, you raise an interesting point. But as I think about it, I suspect that it would have to be fairly similar the Constexpr computation would have to be done in a fairly similar way, because if it used a different, like if it's an embedded platform and the processor is like, say, 16-bit or something really archaic kind of thing, and then you're running on a 64-bit machine, it could probably cause problems. Well, especially the other way around, it could cause problems maybe even more. If you're doing compile time computation with one size of integer and then a different one at runtime. But my suspicion is they probably would have to be the same, which I think is basically kind of what you're asking. Yeah, I never really thought too much about that.
Because I was curious, and the standard specifies minimums but not maximums, so it's lower bounded.
Oh, okay. So they don't necessarily have to be the same size then, just as long as it meets a certain minimum requirement. Okay. Yeah. So I don't know. That could maybe, well, I guess probably they've done it in a way that it won't cause problems. But you could imagine that it could cause some weirdness maybe if things are not even the same size of integer or float or whatever. Okay. And any other questions? Yeah, I guess we finished with that. And then what was this? Oh, okay. In this particular example, maybe just to kind of save some time here. In this particular case, the problem with this particular code is that the return type that we're using is a non-literal type. So if you remember Constexpr functions, they're all the parameters they take and all the return value as well. The types of all these things have to be literal types. Again, a dead giveaway that something's not a literal type, at least with the current state of affairs with Constexpr in the language. If it allocates memory, it's not going to be Constexpr. At least if it's allocated on the heap, like using new and delete and stuff like that, or malloc or whatever. And so this is the case here. There is a good way to fix this. It turns out that the particular code that we're doing here, we're just trying to return a vector that always has 3 elements in it. So because it's always the same number of elements, there's kind of a good workaround, which is probably we're not really using the most appropriate type to begin with. Probably we shouldn't use vector. Probably what we want to use is std array. A std array is an array that's its size is fixed at compile time. So this is an array of 3 floats. The 3 here is the number of elements in the array. But this is a literal type. So it doesn't do any memory allocation and so on. So we could use this at compile time. So in this case, it's a good workaround for this particular problem. And, yeah. Any questions? I'm kind of wondering, like, with 5 minutes left in the lecture, I'm wondering whether I should go on to this new stuff. Well, I guess I probably should anyway, because you might give that one a little bit later. Anyway, so that kind of draws to a conclusion our coverage of compile time computation. So at this point, you have, if you like to work ahead, we've covered enough material that you could do. I think assignment 2 is the one that's on compile time computation, or at least the main focus of it is compile time computation. So at least we covered all the material for that. So the next thing I'm going to be talking about is maybe one of the more technical parts of the course. It basically relates to things like moving versus copying, temporary objects, L values, R values, all these things that kind of strike fear into the heart of many C and C++ programmers. Anyway, but nevertheless, these things are really important. This course is about like trying to write really efficient code and so on. So temporary objects are not things that can be ignored, and also copying versus moving is very important not to kind of ignore, because the implications or repercussions of ignoring this can be very severe in terms of efficiency of code. So first, what I want to talk about are temporary objects. So a temporary object is essentially an object that's introduced by the compiler. There is no variable per se that's explicitly written in your code that you've written. But in order for the compiler to have any reasonable hope of making things work, it has to introduce a variable that wasn't there. It's called a temporary object. It's an unnamed object. It has no name. There's not like a name X. It just has no name. There's no way to refer to it by name. But nevertheless, it exists. Its existence is important because if you create a variable, you have to construct it. If you construct it, you're going to be destroying it later. You have to destroy it. So even if you do nothing with a temporary object, you just bring it into existence and let it die, you have the cost of a constructor call and a destructor call. But typically, there's other stuff that will happen as well. And because of this, things can get even worse than just the overhead of a constructor and destructor call. And constructors and destructors themselves can be very, very expensive as well for some classes. Anyway, so this is why we might care about these things. So temporary objects can be created in a number of different scenarios. So evaluating expressions is one possibility. I'll go through these in more detail with examples. Passing arguments to functions, functions that return by value, create temporary objects. Reference initialization is another situation, binding references. So just to give some examples of these things, Here, suppose that we have std string, which is basically just a implementation of strings in the standard library, basically kind of like an array of characters, for those of you who might not be familiar with it. So here I'm creating a string initialized to hello space and another string here called s2, which is initialized to world. And then this class defines an operator, like a binary plus operator that I can use to concatenate two strings. So s1 plus s2 will be s1 with s2 tagged on to the end of it. Basically performs string concatenation. But if you stop and think about this, how is this really going to work? Like if the compiler didn't do some kind of magical stuff under the hood, how is this going to work? Because when you call like operator plus that actually adds these two strings together, you have to pass it, or it has to, or sorry, I guess the way to look at it is maybe, I don't know, look at this. Kind of, my mind is freezing a little bit here. Well, okay, so really the issue is more with respect to the return value. So like when you call operator plus, like as I was describing, it's going to pass s1 and s2 as parameters, like you're basically operating the binary over operator plus. And it's going to return a string back, which is the concatenation of s1 and s2. And what's happening is that the return value is going to get passed into the assignment operator equals. There's an operator equals defined for the string class as well, which just does what you think. It basically copies one string to the other, or in some cases could move. But the thing is, what is the thing on the right-hand side that's going to be passed as the parameter to operator equals, the assignment operator, the thing that you're assigning from? Because s1 plus s2 is not a thing. Like it's an expression, right? But when you call operator equals, you have to give it something. You have to give it an object that you're assigning from. So like, what's it going to give? It can't just say, well, it's s1 plus s2 in quotes, like something like that. So what happens is the compiler actually creates, even though you don't explicitly ask for it, it will create a new object, which is, in other words, this code here kind of gets replaced by these next two lines here, something kind of conceptually like this. It creates a new object, which is a temporary object. It's not called _temp. It has no name. There's no way that you can refer to it by name. But just to give some kind of equivalent code I can show, it has some object, which I'm calling _temp, which is initialized to s1 plus s2. And then what it does is it instead calls operator equals, passing as the object that you're assigning from is this temporary object. So what's in sort of implied in all of this, in addition to the fact that you're doing the assignment, because you're creating this object, the compiler is going to invoke the constructor for a string to create _temp. And then when you reach the end of the lifetime of that temporary object, it's going to call the destructor. So in addition to the other things we're doing, like the assignment, and the assignment's kind of unavoidable, no matter what, we're going to need to do an assignment. But we're also doing this extra overhead of a constructor call and a destructor to actually create the string and destroy the string. And anyway, so this is maybe might not be something that's immediately obvious to you when you first look at the code until you start thinking about issues with respect to temporaries. But this can sometimes be a quite costly thing. If this is in a loop, maybe, and you're doing it over and over again, maybe the cost of calling the constructors and destructors can be something that would be of concern to you. It could maybe become a bottleneck. Mm-hmm.
Why isn't that constructor step handled by like the plus operator? Because I assume the string class has a custom plus operator.
Yeah, so it has an operator plus that takes basically two strings. And probably their passes, const references, something like that. So you basically the important thing is you have two strings that are going into operator plus, and the return value is a string.
So isn't that handled?
Like, because the problem is not really the plus. The problem is the equals. Like, you need to do the assignment. In order to do the assignment, you need something to assign from, like the source for the assignment operation. And the thing is, what is it? It's not S1. It's not S2. And S1 plus S2 is not an object. It's just an expression in the language. You actually need an object that represents the sum of S1 plus S2. In other words, you need an object to hold the return value of operator plus. But you didn't write that variable, the one that holds the return value, but nevertheless, whether you like it or not, it exists and it's there and the compiler introduces it for you. Because otherwise, the return value of operator plus would just drop off the edge of the earth and you would never be able to access it because it would be gone. Like, it needs to be put somewhere so that it can be passed to the assignment operator as the thing on the right-hand side of the assignment. I guess I better stop here. I'm starting to run over time.